All right, well, hello physics students, and welcome to this video lecture that is just meant to debrief this practice worksheet that we did yesterday in class. So I'm going to go through questions 1, 2, 3, and 4A. 4B is exactly the same as question 3, so but I did want to kind of go through this just to show you this process in terms of how to solve these horizontal and angle launch projectile problems once again. So first things first, question 1 is conceptual in nature. It's asking us to draw motion graphs for the horizontal and vertical directions of an angle launch projectile. So in the horizontal direction, we know that motion is constant. Okay, so that means our velocity is not changing. So if we go back to our work in our kinematics unit in terms of motion graphs, to show a constant velocity on a position versus time graph, we have a constant slope, meaning then that our velocity graph is just a horizontal line. Okay, those two graph shapes are showing us constant velocity. Now, in terms of the vertical direction, we know that there is acceleration, okay? So we have to ask ourselves, okay, on a position versus time graph, what is this acceleration looking like? Well, this angle launch projectile is starting out with a large positive velocity. And as it's rising to the peak, that velocity is getting smaller and smaller and smaller. So what we should be seeing here is a curved shape where our slopes, our positive slopes, are getting shallower and shallower and shallower, right? Now, at the peak, for a brief second in time, we're at 0 meters per second, and then we start speeding up in the negative direction, okay? So we're seeing these negative slopes getting steeper and steeper and steeper, okay? Meaning we're speeding up in that negative direction, okay? Now, on the velocity versus time graph, again, we're starting out with a large positive velocity, so we should be starting up here somewhere. We know at the peak, we're at 0, so the first part of the motion should look like this on a velocity versus time graph, okay? And then to finish this up, after the peak, it starts speeding up in the negative direction. Okay, we get further away from that x-axis, all right? And now in terms of acceleration, well, remember the slope of velocity versus time graph is telling us what acceleration is. This is a constant negative slope, so our acceleration versus time graph should look like this, okay? And that value, we should all know, is negative 9.8 meters per second squared. Okay, so those are the motion graphs for number 1. All right, now, number 2, horizontally launched projectile. I have all of my information in my T-chart. Again, always start these problems out organizing your information X and Y, okay? This helps us separate the two directions. Remember, the two directions are independent of one another. But the variable that we need to find that links our two directions together is time. So that's actually our first step in this problem. We're ultimately trying to find what delta x is. So we need to work in our y direction first to find time. Notice we know 1, 2, 3 pieces of information, so we can find our fourth. So the equation that we can use here is delta y is equal to v initial y times time plus 1/2 at squared. Now remember, v initial in the y direction is 0, so this whole term goes away. All right, and if we plug and chug, plug in the stuff that we know, we should get time equal to 0.55 seconds. Okay, now from there, we can start working in our x direction. Okay, remember, all we have to use in our x direction is our simple constant velocity equation. So from there, we can solve for delta x, and we should get a delta x here of 2.77 meters. Okay, so horizontally launched projectile problems, pretty straightforward. We're going to ramp up the difficulty a little bit on the next slide. All right, so number 3, our lacrosse player. So in this problem, again, that 20 meters per second that I give you is directed at this 30-degree angle. So we have to split up that velocity into its x and its y components. So we have to use trig. Okay, this is your adjacent side, this is your opposite side. So you're using sine and then cosine to get values of 17.3 meters per second for Vx. And for V initial in the y, you're getting 10 meters per second. So again, in this problem, we're trying to find delta x. So we need to find time. We need to find time first. Now, remember, with these angle launch projectile problems, we know a really important piece of information at the peak. Vy is equal to 0, okay? And at the peak, that's the halfway point. So if we can find the time it takes to get from launch to peak, we can just multiply it by 2 to figure out the total time that it's in the air, okay? So what I'm going to do is I'm going to use this guy right here. I'm going to say that my V final in the y is 0 because I'm going to say that that's this point right here. It's the peak, okay? So V final in the y is going to be equal to 0. I know V initial y, and I know my acceleration. So again, we're finding time 1/2 here. We're finding time to the peak. So time 1/2, if we do this correctly, is going to equal 1.02 seconds, meaning that time total is just double that. Okay, so it's going to be 2.04 seconds. Knowing that time, we can now work in our x direction to find delta x. Okay, so we can use our constant velocity equation, rearrange that to solve for delta x, and our delta x is going to equal 35.3 meters. Okay, so really key piece here with these angle launch problems is understanding that we can cut the motion in half, and we know that Vy is equal to 0 at the peak. All right, now 4A is a little unique. So again, this velocity that I gave you is directed at 50 degrees. Okay, so we have to split this velocity up into its x and its y components, same way we did in number 3. All right, now what we're trying to figure out in part A is we're trying to figure out where that balloon strikes the building. Okay, so we cannot make the assumption here that this balloon is striking the building at the peak. We need to figure out first how much time it takes for the balloon to get to the building to then find where it strikes the building, okay? Notice in the y direction, we don't have enough information to find that time it takes to get to the building, but in our x direction, we do. So we can work in our x direction here to find time, okay? We know Vx, we know delta x, so we can find time, which is equal to 2.07 seconds. Okay, so that's the time it takes for the balloon to get to the building. Now we can work in the y direction because we now know 1, 2, 3 pieces of information. Okay, so what we can do is we can use this guy right here. Okay, we know everything. We know V initial and the y. We know time. We know acceleration. We know time. So our delta y here then is going to equal 7.53 meters. Okay, that means that this projectile is hitting the building 7.53 meters above the ground. So really, this balloon is actually hitting the peak before it reaches the building. Okay, so the path kind of looks like this. All right. Now, part B is essentially the same as number 3. So if the building weren't there, you're just finding what the range of the balloon would be, okay, what the delta x is. So that's exactly like problem number 3. All right, so there's the process on how to go through these problems. I hope this was helpful. If you have any questions, please come talk to me. Take care, physics students.